Welcome to the 10th lecture. We are studying Poisson processes, and today we will study merging of Poisson processes. Here is a machine, we call it a merger, in which we enter a number of Poisson processes. There are 10 in total, there are n in total, and this merger merges these processes randomly, picking arrivals from any of these n processes, and has one output, which is the merger of these n Poisson processes. If the first process has a parameter lambda 1, the second lambda 2, and the final lambda n, the merged process has one parameter, that is the sum of all these processes. Another assumption that we make for these n independent processes is that if x1 is a random variable that belongs to this distribution, x2 is another random variable that belongs to the second distribution, and xn is a random variable that belongs to the nth Poisson process, then x1, x2, x3 and xn are independent of each other. They are independent random variables. So what should be the expected value of this merged process? We know that the expected value of this process is lambda 1 times t. We have already studied that, lambda 2 times t, and for this is lambda n times t. So what should be the expected value of x, where x belongs to lambda 1, lambda 2, lambda n, lambda 1 plus lambda 2 plus lambda 3 plus up to plus lambda n. This should be, since they are independent, expected value of x for this process plus expected value for the second process and the expected value for the final process. Why? Because they are independent of each other. Similarly, the variance of the merged process is variance of lambda 1, variance of the first process plus variance of the second process, finally variance of the last process. Right, but there is a special case where we have all these lambdas equal. If we have a special case where all lambdas, lambda 1, lambda 2 up to lambda n, they're all equal, and we call them lambda. Special case is where lambda 2, lambda 3, they are all equal. So what should be the parameter of the merged process? This should be Poisson of n lambda, and since they are all independent, that should be n times the expected value of any of the process. And the variance would also be the variance of lambda plus lambda plus lambda of x would be n times variance of any of the n processes. Right. What should be next we will talk about the inter-arrival time of the merge process. Inter-arrival time. Inter-arrival time, we know that for a Poisson process, inter-arrival time is modeled by our distribution. We call it exponential distribution. It's modeled by exponential distribution. For merge process, we know that a merge process is also a Poisson process, but with parameter and lambda. If all lambdas are the same, this is a Poisson process. The merge process is also a Poisson process with parameter n lambda. And we know that if it is not n lambda, it's a single process, it's only lambda, the expected value of the inter-arrival time is if we have this parameter lambda is 1 over lambda. So if we have this n lambda instead, in case of a merged process, this should be 1 over n lambda, right? And the variance of the inter-arrival time, if the parameter is lambda, this is 1 over lambda squared. So if we compute for n lambda, this is 1 over n lambda squared. Right. So after talking about merged process and inter-arrivals in merged Poisson process, now we are going to solve a problem. An example where we have some light bulbs whose lifetime light bulbs and lifetime of each bulb is an exponential RV and a variable with rate lambda. The lifetime of each bulb, right? Lifetime of each bulb is an exponential and a variable with rate lambda. Now we are required to find, suppose we are given 8 such bulbs. Suppose we are given 8 such bulbs and we are asked to find the time until third light bulb goes off, reaches its lifetime. So it can be thought of as a timeline where at time t1 is the time at which the first bulb goes off, T2 is the time where the second goes off, and T3 is the time where the third goes off. Right, starting from some initial point 0. So the parameter, it's a Poisson process. The parameter of the process is 8 lambda here and lambda, and all lambdas are the same because all light bulbs are equal, are like, and the parameters from 0 till the first light bulb goes off is 8 lambda. But once one light bulb goes off, this parameter becomes 7 lambda, and once second goes off, it becomes 6 lambda. So we are asked to find the expected value of the time, the expected time at which third light bulb goes off. This should be the expected value, since they are all independent of each other. Whatever happens here is independent of whatever has happened here, and whatever happens here is independent of what has happened before. So this should be expected value of the first light bulb goes off plus the expected value of the expected time where second light bulb goes off plus the expected time where the third light bulb goes off. So if we add the expected value, we know that for a geometric, since this is the interarrival time, we'll model it using geometric distribution. So for time 1, the parameter is 8 lambda. We can also mention it here. For this is 6 lambda, and for this is 8 lambda, for this 7, and for this is 6 lambda. So now we are ready to compute this expected time till the third failure. Is expected value of the geometric distribution of the failure with parameter 8 lambda. 1 over 8 lambda. For this is 1 over 7 lambda, 1 over 6 lambda. And in part B, we are required to find the variance of the variance of the time till third failure. So the variance of the time till third failure, since these processes are independent, or all intervals are independent, so all intervals are independent, so variance of T1 where the parameter is 8 lambda, variance of time T2 where the parameter is 7 lambda, plus the third where the parameter is 6 lambda. So this is 1 over 8 lambda squared, 1 over 7 lambda squared, plus 1 over 6 lambda squared. Right. This is all for today's lecture, and in the next lecture we will keep on studying Poisson processes. Thank you.